All right, let's talk about linear operators. What's an operator? To answer that, you first have to think about what's a function. What's a function? Function is something that you plug in one thing, you get the other, right? You have the input and it gives you an output. In a way that you can't have two different outputs for a single input, right? So as long as that's consistent, then you say it's a function, right? You get one unique output for one unique input. That's what a function is. What's an operator? Well, operators are just like functions, but we use the word operator to say that it's like a function where the input is a function and output is a function. Okay, so if you have a function which you take an input as a function and you create a new function from the old and you get it back, that's what you call an operator. You've worked with operators before. What kind of operators have you worked with in calculus? What's something that gives you a new function from the old? Huh? What?
Like the Euler stuff?
No. Derivatives, right? Differentiation is an operator. Okay. So differentiation is an operator because you take in a function and it differentiates and it gives you back a new function, right? Yeah. So differentiation is an operator, and not only just a single differentiation, the partial derivatives are operators. Any constant multiples are operators. Any order of differentiation is an operator. You can have a second order differentiation that's an operator because it takes in a function and gives you back a function. So anything that takes a function as an input and gives you back another function as an output, that's an operator. But there are special classes of operators called linear operators. What are these linear operators? Well, so if L is an operator, linearity means the following. Linearity means that if you apply L to C1 f of x plus C2 g of x, so you have two constants and two functions, then it has the property that L can be applied to each individual functions, just like this. If summations can be split, and also if the constants can come out, you call such an operator a differential, a linear operator. So you call this property linear. And the differential operator that we know all satisfies this, right? Partial derivative, second order differentiation, first order differentiation. Any differential operator that you know of has this form, right? There are some other ones, but we don't care. The only kind of linear operators that we will care about are the operators of the following form. If you have something like so example, if you have an operator that looks like 5d squared minus 6x times d plus, let's put something horrible, e to the x minus x. If you say this is L, that's an example of a differential, that's an example of a linear operator. Okay? You can check that indeed this is linear. It's actually a combination of two types of operators. These D's are differential operators. You differentiate once with respect to x. And these are multiplication operators. So whatever function you're given, you just multiply this and you create a new function. Okay? And multiplication operators and differential operators, or any combination of those, will always be linear. Okay? Yeah, just to see that it does work, let's try it. I think this is too complicated for a simple example, but I can't go back and change. All right, let's just go try this one. L applied to C1F plus C2G. What does that give us? All right, this is 5d squared minus 6xd plus e to the x minus x. That's what I claimed my L to be. I tried to say this is my L applied to C1F plus C2G. Then when this hits this one, what happens? Second order differential operators are linear, so all the constants can be pulled out. I can differentiate these separately, right? So this is C1 times 5 times F double prime plus C2 times 5 times G double prime. So this is what you get if you apply 5d squared to this one. Now how about this one? Okay, plus if negative 6d hits this one, this is what it does. First, d hits f, so you differentiate once. And negative 6x is multiplied. And then negative 6xd, when it hits this one, you differentiate once and you multiply negative 6x. That's what this operator does. And finally, when this is multiplied to this, it's just distribution, right? So this times this times this, and you can pull the C1 in front, so it's C1 times e to the x minus x f plus C2 times e to the x minus x g. And then if you collect the ones with C1s, if you collect the ones with C2s, you will see that what you get is exactly same as what you would have gotten if I applied L to F and L to G separately and multiplied these two. Okay, so I'm skipping some steps here because it's getting boring, but if you actually computed this and this separately and multiply C1, multiply C2 and add them together, you'll see that they are indeed the same. Okay, so that's an example, and in fact anything that looks like the following, any some function of x, or it could be a constant, times d squared, some function of x, or it could be a constant, times d, plus another constant or a function of x, that will be considered as a linear one. And you could also have higher order linear operators with like third order, d cubed, d to the fourth, all these you could have, okay? All right, so that's what linear is. And it's important for us to know that the operator that we're working on is a linear operator, because let's go back to the example that we just did, which was y double prime minus 3y minus 4y equal to 0. Now this could be thought as, Ly equal to 0, with L being equal to what? Can you tell me what L is?
0.
Now, what operator is on the left? What's the operator on the left side? I just wrote it.
C1 L f of x.
Oh, that's
D2.
Yeah, D2. That's the operator, right? That's the operator on the left side. If you apply this operator to y, then it becomes exactly this, right? That's the operator. And then because this is a bunch of differential operators and constant multiples, it is linear. Okay? Now, why is that important? Well, here's why it's important. I can just make guesses and come up with solutions of this. Okay? And I probably told you before, but for these type of equations, we can always take e to the rx as one of the solutions. And I mean, this is the experience you get. You at some point you gain the experience that any constant coefficient linear homogeneous differential equation will have the solution that looks like exactly this. Okay. So we know this, then we just plug this in and figure out what values of r is going to give me the exact solution. So let's do that. If I differentiate this twice, what do you get? Every time you differentiate, r comes down, right? So you get r squared e to the rx. And differentiating once gives you just r. So you end up with r squared e to the rx minus 3r e to the rx minus 4 e to the rx equal to 0. And if you factor the e to the rx out, you end up with r squared minus 3r minus 4 equal to 0, which in turn becomes r minus 4 times r plus 1 equal to 0. See, exponential functions can never be 0, so the only way this equation can hold is when this part is equal to 0, but that's a quadratic equation which you can factor. If you factor, you get r equals to 4 and negative 1, which means what are the two solutions that's possible? E to the 4x and e to the negative x, right? Okay. So here is what we have. We found out that if I apply this L here to e to the 4x, what are we going to get?
0.
Yeah, because if I have e to the 4x in here, it's going to create 0, right? So applying this to that means it's like plugging e to the 4x to the left side. That's the same as, these two things are the same. Applying this differential operator to this and plugging this in the left side are exactly the same thing. Okay, it's exactly the same. Therefore, we know that it's equal to 0. Okay. What about L times e to the negative x? What would that give me?
0.
0 again, because again, if you plug it here, we know that it's going to create 0. Okay. Now, that means we are very close to the entire solution, because if L of e to the 4x is 0 and L of e to the negative x is 0, then because of this linearity, we can say C1 times e to the 4x plus C2 times e to the negative x, and you apply the L, according to this calculation, is C1 times L applied to e to the 4x plus C2 times L applied to e to the negative x, and therefore, what is this? Times 0, C2 times 0. So at the end of the day, what do you get?
0.
0, meaning that this is the general solution. Okay? So that's the amazing story that we have. Once you know that what you're dealing with is a linear operator, then we can say, therefore, y equals to C1 times e to the 4x plus C2 times e to the negative x is a general solution to that. Of course, after this, we still have to use the Wronskian to show that these are in fact linearly independent, so that these are genuinely different functions, and therefore this does produce a family of solutions with two free parameters, and then the mathematical theory which says, oh, these differential equations always have a solution, and it is unique given two initial conditions. These theorems guarantees that what we have here is indeed the solution we want. But of course, when we solve equations like this, we will always, not always, unless we are told to verify it, we'll just shut our mouth and say, hey, here's one solution, here's another solution, here's the linear combination, that's all the solutions, done. We happily go. Without having to do all the calculations that we have to do, we can just settle on just making guesses and justifying. So that's the entire story.